Have you ever stopped to really think about the materials around us every single day? You know, the glass in your window, the fibers in the clothes you're wearing, the metal and plastic in your phone. We just kind of take them for granted, don't we? But what if those materials weren't so static? What if they could, like, literally reshape themselves on command? Or conduct electricity way faster than anything we know? Or even act as this invisible super light shield against, say, intense heat? It feels like we're right on the edge, you know? Standing on the precipice of a completely new era for materials here in the 21st century. We're going way beyond just mixing stuff together to make better composites, things that are stronger or lighter. Now it seems like we're learning to actually manipulate and harness the really unique behaviors of matter at its most basic levels, like the nano and mesoscale. It's a pretty profound shift, actually, a fundamental rethinking of how we engineer the actual stuff our world is made of. And it feels like it's happening fast right now.
That's exactly it. It's not just making things a little bit better, like slightly stronger steel or more flexible plastic. This is a real paradigm shift. The usefulness of a material isn't just about its bulk properties anymore, how dense it is overall, or how stiff it feels, or what it looks like. Instead, we're diving deep, looking at the precise atomic structure, designing intricate porosity, maybe even embedding the ability to process information right into the material itself. We are quite literally rebuilding matter from the ground up, atom by atom, essentially,
Yeah.
trying to get functionalities that honestly used to sound like pure science fiction.
Okay, so that's our mission for you today. We've got this stack of sources articles, some really cutting-edge research, your own notes too, and we're going to do a deep dive into three specific materials that seem poised to, well, maybe redefine our world. We're talking graphene, aerogel, and programmable matter. Our goal is pretty straightforward. Pull out the most important bits of knowledge, help you really grasp their revolutionary potential, and also explore the journey, the complex path from a lab discovery to actually being used everywhere.
Right. And we'll definitely try to go beyond just, describing what they are. We want to critically look at the factors that will determine if they succeed or, what holds them back, and also look at how they connect, the intercessions and maybe synergies between them, which are often overlooked. Because as you'll see, the future probably isn't just about one single miracle material. It's more about how these materials can work together, combine, maybe even boost each other's capabilities.
Okay, good point.
Yeah.
So before we really dive in, let's just quickly set the stage. Define these materials of tomorrow for everyone listening. Make sure we're all on the same page. First up, graphene. Often called the classic 2D material, right? Imagine just a single layer of carbon atoms, one atom thick, arranged in that hexagonal honeycomb pattern. It's supposed to be incredibly strong, superconductive, and also transparent. Then there's aerogel, nicknamed frozen smoke, which sounds cool. This is apparently a synthetic ultra-porous solid. It's made of what? Mostly air, like 50 to nearly 100% air. And it holds records for being super light and also an amazing insulator. And finally, we'll get into programmable matter. This one sounds the most conceptual, futuristic. It's basically a field looking at materials designed to actually change their physical properties like shape, density, stiffness in a controlled, programmable way, maybe based on user input or sensing the environment. So yeah, get ready for maybe some aha moments, because you're going to hear about materials that really do sound like science fiction. But the thing is, they're already starting to make an impact now, and they seem set to define our future in ways we're probably just beginning to imagine. All right, let's unpack this.
Graphene, the epitome of 2D power.
Okay, let's start with graphene. You called it the epitome of 2D power. So what is it exactly? It's carbon, sure, but what makes it so special right down at the atomic level?
Right, you've hit the core of it. Its amazing properties really do stem directly from that unique atomic arrangement. Just picture it again, that single flat layer of carbon atoms in that perfect hexagonal honeycomb lattice. Think of it like microscopic chicken wire, maybe,
Yeah.
where every intersection is just one carbon atom. But it's not just a neat pattern, it's the absolute blueprint for how it behaves. The real magic, scientifically speaking, is in that structure. Each carbon atom bonded tightly to three neighbors within the same flat plane. These are really strong bonds, sigma bonds, formed by something called sp2 hybridization, basically how the electrons arrange themselves. And it's this exact bonding and geometry that gives the whole lattice its incredible strength, its flexibility, and those unique electronic properties. And the thickness, we're talking almost impossibly thin, like 0.334 to 0.345 nanometers.
Nanometers. That's hard to even picture. How thin is that compared to, say, a human hair?
Oh, vastly thinner. A human hair is maybe 80,000 nanometers thick, something like that. So graphene is truly Genuinely, a single atom-thick material, the thinnest thing we know how to make.
Wow. Okay, that scale is just mind-boggling. Thinner than anything we can really visualize. But it's this unique 2D structure that unlocks those record-breaking properties everyone talks about. Let's start with electrical properties. That seems to be where graphene really shines.
Absolutely. Electrically, it's extraordinary. Graphene shows exceptionally high electron mobility, measured up to 200,000 centimeter vis.
Okay, 200,000. Well, what does that mean in practice? How does that compare to, say, silicon in our current chips?
Great question. Silicon, which is, the foundation of modern electronics, typically has an electron mobility around 1,400 centimeter Hauss-Vis. So we're talking electrons moving potentially over 100 times faster in graphene. And it's not just speed. These electrons and the holes they leave behind near what's called the Dirac point act almost like, well, massless fermions is the technical term. Basically, they behave as if they have almost no mass. Imagine trying to stop something with no weight. This means they zip through the material with virtually no resistance, hitting speeds close to 106 meters per second. That's, about 1,300th the speed of light? Still incredibly fast for an electron in a solid. This makes graphene potentially revolutionary for semiconductor devices that need super fast response times, pushing computing way beyond silicon's limits, things like terahertz electronics, data processing speeds we can barely imagine right now. Now, there's a slight catch. Single-layer graphene, SLG, is technically a zero bandgap semiconductor that limits some direct transistor uses.
Zero bandgap, so it's always on. Hard to make a switch.
Kind of, yeah. But interestingly, in bilayer graphene, BLG, just 2 layers, you can actually create a tunable band gap by applying an electric field. So that dramatically expands its potential for more complex electronic circuits. It's quite clever.
That is genuinely incredible speed. Orders of magnitude faster electronics. But it's not just electricity. Graphene also has the highest thermal conductivity known, right? How does that help in the real world?
Indeed. Its ability to conduct heat is also off the charts. Measured thermal conductivity for suspended graphene, just floating, is somewhere between 2,600 and 5,300 watts per meter Kelvin.
Okay, again, comparison. What's copper, which we think of as a good heat conductor?
Copper is around 400 WRNK, so graphene is, 10 times better, roughly, just vastly higher than any other material. Even when graphene is supported on something like a substrate, which can slow it down a bit, its conductivity is still typically 370 to 600 WNK. Still comparable to or better than many metals. The implications for heat management are huge. Think about tiny, powerful processors in our phones, our laptops. Heat is often the bottleneck, right?
Definitely. My laptop fan kicks in all the time.
Exactly. Graphene could revolutionize cooling. Allow for smaller, more powerful electronics that last longer because they don't overheat. Or maybe help dissipate heat on spacecraft in extreme environments, just much more efficiently.
And mechanically,
yeah.
This super thin sheet is also supposedly unbelievably strong, yet flexible. That seems almost contradictory.
It does seem weird, yeah, but that's part of its magic. Its Young's modulus, that's a measure of stiffness, is reported around 1 terapascal, 1 TPa.
Terapascal, is that a lot?
It's enormous. Steel, which we think of as strong and stiff, is typically around 200 gigapascals. So graphene is roughly 5 times stiffer and stronger, adjusted for weight. But despite that incredible strength, it's also incredibly flexible. You can bend it, stretch it quite a bit, and it doesn't just snap. Imagine wrapping something in a material 5 times stronger than steel, but only 1 atom thick. That's the kind of engineering potential we're looking at. That combination is really unique.
Plus, it's practically invisible, right? Nearly transparent. That must open up even more possibilities.
Optically, yeah, it's almost transparent. It lets through about 97.7% of visible light, which is amazing for something made of carbon. And that property is absolutely critical for tons of modern devices, especially things that need both transparency and electrical conductivity. Think touchscreens, solar cells.
Right. You need to see through it, but it also needs to conduct the signal.
Precisely. Graphene lets you have that highly conductive, strong layer without blocking the view.
So, okay, let's recap. Record-breaking electrical and thermal conductivity, incredible strength and flexibility, and it's transparent. When you put all that together, it's not just about making current tech a bit faster or stronger. It feels like it enables totally new kinds of devices, like electronics woven into your clothes, or maybe brain interfaces that can work seamlessly with our biology. It's like reimagining the device itself, isn't it? That's an almost unbelievable package of properties, pushing the limits of what we thought materials could do. But how is this lab marvel actually, translating into the real world? Where are we seeing graphene move beyond just theory and actually start driving innovation? What industries are using it?
It's definitely moving out of the lab. Graphene is popping up everywhere, from basic research right through to industrial prototypes that are already shaping products. Take optoelectronics, that's a big one. Graphene is looking like a really compelling alternative to something called indium tin oxide, ITO.
ITO. That's in most touch screens now, right?
Exactly. It's what makes your phone or tablet screen work. But ITO has downsides. It's kind of brittle, screens crack easily, it's relatively expensive, and indium itself is a somewhat rare element with volatile supply chains. Graphene, being transparent and highly conductive, plus flexible and strong, could be a much better, more sustainable alternative. This is a potential game changer for flexible touchscreens, LCDs, OLED displays. We're talking about genuinely rollable e-paper, phones that can fold without the screen cracking, flexible electronics you could wrap around things. These aren't just possibilities anymore. They feel almost inevitable thanks to graphene.
Okay, no more cracked phone screens. Sign me up. That sounds amazing.
Oh.
And the energy sector. That seems like another huge area where graphene could make a massive difference both for generating power and storing it.
Absolutely huge. It's like a dual revolution waiting to happen there. For solar energy, graphene has been used cleverly to make pretty inexpensive solar cells, Schottky junction types. Some nanostructured graphene photovoltaics have already hit over 12% efficiency in single cells, which is pretty good. But here's where it gets really exciting. Graphene has this unique quantum property where it can potentially generate multiple electrons from a single photon of light it absorbs. It's called multi-exciton generation.
Multiple electrons from one photon. Normal solar cells only get one, right?
Exactly. If they can harness this property effectively, it could theoretically lead to solar cell efficiencies up to maybe 60%. That blows current silicon limits out of the water. Plus, because graphene is so incredibly light and thin, it makes solar power viable in places where heavy, bulky, traditional panels just aren't practical. Think remote areas, temporary setups, maybe even integrated into building materials seamlessly. Imagine rolling out a solar blanket to power a village.
Wow, 60% efficiency would be incredible. And beyond generating power, what about storing it? Faster charging, longer-lasting batteries? That's the dream for everyone, isn't it?
It really is. And graphene's properties, high conductivity, large surface area, chemical stability, are perfect for improving energy storage. We're talking about enabling batteries and supercapacitors that can charge much, much faster and also last for significantly more charge cycles, meaning longer lifespans.
So charging my phone in minutes instead of hours.
Potentially, yes. Or think about electric vehicle batteries that could last for hundreds of thousands of miles without degrading much. That would make EVs truly competitive. Maybe even superior to gasoline cars in terms of lifetime cost and convenience. Graphene can dramatically increase the effective surface area of electrodes and improve how ions move within the battery, leading directly to those faster charging times and longer cycle lives. It tackles some of the biggest frustrations with current battery tech head-on.
The environmental side seems really significant too, moving beyond just gadgets and tackling bigger problems.
Definitely impactful. Take water purification. Graphene oxide membranes, which are slightly different but related, have this amazing property. They let water vapor pass through really easily, but they block almost everything else. Liquids, dissolved salts, even most gases.
So you could use them for desalination, making seawater drinkable.
Exactly. It's already been shown to be highly effective for desalination and general water purification. And these graphene membranes can be like 1,000 times thinner than conventional filters. That means you can potentially get much more clean water faster using less pump pressure, which means less energy. A potential game changer for water-scarce regions. Also, think about protective coatings. Graphene-based coatings can protect surfaces from corrosion, wear, UV damage, making products last much longer. That reduces waste, saves resources, less material consumption overall. Useful in everything from ships to cars to buildings.
And what about bioengineering? How does this carbon sheet interact with, our bodies?
That's another fascinating area. Its unique combination, large surface area, great electrical conductivity, thinness, strength, makes it excellent for developing really fast, efficient bioelectric sensors.
Sensors, like what could these sense?
Imagine maybe a tiny flexible graphene sensor in a contact lens that monitors your glucose levels non-invasively. Or a patch on your skin continuously tracking your hemoglobin, or maybe even specific DNA markers in real time. Researchers are also looking at it for nerve regeneration scaffolds, targeted drug delivery systems, highly sensitive diagnostic tools. Its biocompatibility seems pretty good, and its electrical properties make it uniquely suited to interface with our biological systems at a very fundamental level. It really opens doors for personalized medicine, proactive health monitoring, stuff we've only dreamed about before.
Wow. Okay, so from screens that won't break to cleaner water for more people, faster charging, more efficient energy, even monitoring our health. Graphene really does sound like a superstar material. It's redefining what we thought carbon could do. But okay, despite all this incredible promise, this amazing potential, the road from the lab to, being everywhere isn't always easy. What are the big challenges graphene is facing right now? Why isn't it already in everything?
That's the crucial question, isn't it? Because the path to commercialization is definitely bumpy. The main issue really boils down to production pains. First and foremost, there's the challenge of high cost. Producing that really high-quality, pristine graphene using methods like chemical vapor deposition, CVD, is still pretty energy-intensive. It often needs expensive raw materials, specialized equipment.
So it's just expensive to make good stuff in large amounts.
Exactly. That makes it tough to compete economically with materials that are already established and much cheaper to produce, even if graphene performs better.
And getting it out of the lab into industrial scales while keeping that amazing quality. That sounds like a balancing act. Is there a trade-off between quantity and quality?
There really is a fundamental tension between scalability and quality. The method that first got people excited, mechanical exfoliation, basically using sticky tape to peel off layers that can give you amazing high-quality single layers. But it's incredibly slow, painstaking. You can't make tons of it that way. On the other hand, methods that are more scalable, like liquid phase exfoliation or reducing graphene oxide, can produce larger amounts, but the quality often isn't as good. You get inconsistencies, defects, multiple layers mixed together, and that degrades the performance.
And consistency is absolutely key, right?
Yeah.
Especially for things like electronics or medical devices. You need every batch to be the same.
Absolutely vital. Getting uniform layer counts, consistent sizes of the graphene flakes or sheets, high purity, doing that reliably at an industrial scale is still a major hurdle. Even tiny imperfections, defects in the atomic lattice, or leftover chemicals from production can dramatically mess up those fantastic electrical, thermal, and mechanical properties. That makes industries hesitant. If they can't rely on consistent quality, they're not going to switch over their production lines.
Okay, so production is tough. What about the market itself? Is there resistance from existing industries, lack of standards?
The market for graphene is definitely growing. Projections are pretty optimistic. Compound annual growth rates predicted anywhere from nearly 20% up to over 35% between now and the early 2030s, so there's interest. But it still faces real pricing pressure from established materials, like that ITO for touchscreens we mentioned. ITO might not be perfect, but it has decades of optimized production behind it, a mature supply chain. It's the devil they know, basically. Plus, there's a general lack of universally accepted standards for producing and even characterizing graphene. How do you measure its quality consistently? Without clear standards, it's hard for buyers to know exactly what they're getting, which adds risk and slows adoption. It's still a bit like the Wild West in some ways.
Okay. That leads to a really important, maybe slightly uncomfortable question, the environmental paradox of graphene. We talk about all its great sustainable uses, better batteries, solar cells, water filters. But if making it involve toxic chemicals or lots of energy, are we just, shifting the problem? Is the green story more complicated?
That's a vital point. And yes, the picture is often presented as simpler than it is. You're right. Some of the methods for making high-quality graphene do currently involve processes using harsh chemicals, strong acids, powerful solvents. These raise real concerns about worker safety, waste disposal, and potential environmental contamination if they're not managed extremely carefully. And there have been studies showing that if graphene oxide nanoparticles, for example, get into water systems, they can be quite mobile and might interact with aquatic life in ways we don't fully understand yet, potential risks to ecosystems, and maybe human health down the line. So yeah, while the end use might be green, we absolutely have to look critically at the production side. And this really highlights a crucial challenge for this whole field of advanced materials, not just graphene. You can't just judge a material's green credentials based on its final application. You absolutely need a full life cycle analysis. That means looking at everything: where the raw materials come from, the energy and chemicals used to make it, how it performs during its useful life, and crucially, what happens at its end of life. Can it be recycled? Does it break down safely? Only by looking at that whole picture can we really know if we're making genuine progress towards sustainability or just, shuffling the environmental burden around. Finding greener, cleaner production methods is a huge area of ongoing research right now.
Aerogel. the porous champion of insulation.
All right, let's move on from the incredibly thin world of graphene to something almost opposite in structure. Aerogel, the frozen smoke. This stuff seems to defy common sense. How can something that's mostly empty space, famously light, also be the world's best insulator? It feels like it shouldn't work.
It does seem counterintuitive, doesn't it? But that's precisely where its genius lies. Aerogels are this amazing class of synthetic materials. Ultralight, yes, and highly, highly porous. They basically start life as a gel, like gelatin, a solid network trapping liquid inside. But the key trick is replacing that liquid component with a gas, usually air, and doing it so carefully that the delicate, solid structure of the gel doesn't collapse, it stays intact.
Okay, so it starts wet and you dry it out, but how do you stop it from just shriveling up like a raisin or collapsing into a dense solid?
That's the clever part. It involves some smart chemistry and physics. The main method usually starts with something called the sol gel process. You make a colloidal suspension, usually of tiny silica particles, often from a silicon precursor dissolved in alcohol. Then you add something to make it gel, forming a wet gel, this solid silica network holding the solvent. Now comes the critical step, drying it without wrecking the structure. The traditional way is supercritical drying.
Supercritical, what does that mean?
You basically heat the liquid solvent inside the gel and pressurize it, taking it beyond its critical point on the phase diagram. In this supercritical state, there's no distinction between liquid and gas anymore. So you can then gently vent this fluid out without ever forming a normal liquid-vapor boundary. It's the surface tension at that boundary during normal evaporation that would pull the delicate structure inwards and cause it to collapse. Supercritical drying avoids that completely.
Ah, okay. So it avoids the forces that would crush the pores.
Exactly. It preserves that intricate, porous network. Another method gaining ground, because it can be less energy-intensive, is freeze drying. You freeze the solvent solid within the pores, then use a vacuum to make the ice turn directly into vapor sublimation, again avoiding that damaging liquid phase. And aerogels aren't just made of silica. You can make them from other inorganics like alumina or organic polymers, carbon, even from biopolymers now. And the result of this careful process, materials with truly unrivaled properties. They are phenomenal thermal insulators, mainly because they are, as you said, mostly gas, anywhere from 50% up to a staggering 99.98% air by volume. And air itself is a terrible conductor of heat. But it's more than just trapped air. The aerogel's complex, nano-sized porous structure also stops heat transfer by convection. The air molecules are trapped in tiny pockets and can't easily move around to carry heat. Silica aerogels, for instance, have incredibly low thermal conductivity, typically 15 to 50 milliwatts per meter Kelvin.
Okay, 15 to 50. How does that compare to, say, normal insulation like fiberglass?
Oh, much, much better. Fiberglass might be around 40 mMK, good foam maybe 30, but aerogel can get down to 15, even lower in some cases, and often in a much thinner layer. For comparison, a standard glass window pane is maybe 1,000 mMK, so aerogels is vastly superior. Imagine a building wall that loses almost no heat, even in extreme cold, using insulation that's super thin. That's the kind of radical energy-saving potential we're talking about.
That is genuinely amazing. So it's mostly air, which makes it super light. What other physical properties make it unique?
Exactly. That synthesis leads to solids with incredibly low density, sometimes as low as 0.0003 grams per cubic centimeter. Makes them the lightest solid materials known. We mentioned graphene aerogels later, but some of those have been made weighing only 20.16 milligrams per cubic centimeter. That's literally 7 times lighter than air itself.
Lighter than air, but it's solid.
Yeah. You can balance a piece on a flower petal without bending it. It's wild. Beyond lightness, they have extremely high porosity, usually over 90% empty space. And because of all those tiny pores, they have an immense internal surface area, often over 800 square meters, packed into a single gram of material.
800 square meters per gram, that's like a football field of surface area in a teaspoon.
Pretty much. And that huge surface area is another key property. It makes them fantastic for applications needing surface reactions, things like catalysis, absorbing pollutants from air or water, advanced filtration.
Okay, the possibilities for energy saving, lightweight design, they seem almost limitless. It really challenges what we thought was possible. Could change everything from buildings to clothes. So with these incredible properties, where is aerogel actually being used today, and what's next for it?
It's definitely making inroads, especially in high-value areas. The construction sector is a big one. Aerogels are starting to revolutionize sustainable building and energy efficiency. You find them used in high-performance insulation boards, insulating blankets, even mixed into plasters or used in energy-efficient windows and skylights. Putting aerogel insulation in a wall can cut its heat loss, its U value, by nearly half compared to traditional stuff, often while being much thinner. That translates into really significant energy savings over the life of a building, maybe 30 years or more, and big cuts in CO2 emissions. Think about your heating bills, the comfort of your home, and the overall carbon footprint. It's a huge lever.
That's massive for energy consumption and climate goals. And I know NASA has used aerogel for ages, right, for space missions.
That's right. NASA was an early adopter. In aerospace and high-performance textiles, where being lightweight and having top-notch thermal properties is crucial, aerogels are invaluable. NASA famously used silica aerogel on the Stardust spacecraft to capture cosmic dust. Its delicate, porous structure acted like a super gentle catcher's mitt for tiny, fast-moving particles from space, slowing them down without destroying them so they could be brought back to Earth for study.
Wow, catching comet dust.
Exactly. And they used it for thermal insulation on the Mars rovers, protecting the electronics from the brutal temperature swings on Mars' freezing nights, warmer days. And closer to Earth, in the oceans, the U.S. Navy uses aerogel technology in undergarments for deep-sea divers. Provides amazing thermal protection in freezing water, keeping divers warm and safe, but critically, it stays flexible and breathable, which is essential for them to actually do their job effectively. And that really makes you think, doesn't it? If it can protect astronauts on Mars and divers in the deep ocean, what could it do for your regular winter coat or your hiking boots? Integrating aerogel into performance apparel is a really exciting area. It promises clothing that's much warmer, but also lighter, less bulky, and more breathable than traditional insulation like down or fleece. It could genuinely redefine winter clothing for everyone.
Okay, sounds amazing. Incredible properties, really diverse uses, from buildings to spacesuits to maybe my next jacket. So why isn't it everywhere already? If it's so good, why isn't every building wrapped in it? What's holding aerogel back?
That's the million-dollar question, isn't it? And it really comes down to what people in the industry call the battle of two bottlenecks. Now, the economic outlook for aerogel is definitely promising. The market's expected to grow pretty fast, maybe around 15–16% compound annual growth rate over the next decade or so. And that growth is fueled by this big global push towards eco-friendly, energy-efficient materials. Plus, you have governments putting in supportive policies, stricter green building codes. The demand is there, and it's increasing. But the first and still the biggest bottleneck is the high initial production cost. Those complex manufacturing processes we talked about, especially that supercritical drying, there's still a significant barrier. They use a lot of energy, take time, need specialized, expensive equipment.
So it just costs a lot more upfront than, say, fiberglass insulation.
Yeah. Significantly more, yeah, per volume or per insulating value. That creates a big initial investment hurdle for builders, manufacturers, consumers. And this leads to that classic dilemma, right? Long-term value versus the initial spend. While that upfront cost for aerogel can be steep, detailed life cycle studies are increasingly showing that the long-term benefits really do add up. You get those drastically lower energy bills year after year. You get better comfort inside the building, plus the environmental benefits of reduced emissions. Over the lifetime of the building, these savings are starting to outweigh that higher initial price tag more and more often. And as building codes get tighter, energy prices keep rising. The payback time for aerogel just gets shorter and more appealing. So the trend is definitely moving in the right direction. As manufacturing gets more efficient, scales up, maybe find cheaper drying methods, we'll definitely see aerogel become more common, moving from just niche uses into the mainstream.
Programmable matter, redefining form and function.
All right, let's shift gears now to something that sounds even more out there. Programmable matter. This isn't just about what a material is, but what it can become. Dynamically, on demand. It sounds like pure sci-fi, but apparently it's a real scientific frontier.
It definitely pushes the boundaries, yeah. That's a great way to frame it. At its heart, programmable matter is material that's been engineered, designed to actually change its fundamental physical properties. Things like its shape, its density, how stiff it is, its conductivity, maybe even its color. And to do that in a controlled, predictable, programmable way. And that change could be triggered by, say, user input pressing a button, a voice command, or it could happen autonomously with the material sensing changes in its environment and reacting intelligently on its own. The really profound idea here is thinking about material itself as being capable of processing information inherently. And that raises some fascinating questions, doesn't it? Like, what if your jacket could just adapt to the weather, automatically get warmer or more breathable?
Or my phone could change shape, become a bigger screen when I need one.
Exactly. Or morph to fit your hand perfectly.
Yeah.
The theoretical ideas behind this field generally fall into two main schools of thought, two approaches.
Okay, what are those two main approaches?
Well, the first one is maybe easier to grasp. It involves external control. Here, the material's properties are changed by some kind of external stimulus applied to it, like shining a specific light pattern on it, applying a voltage across it, or using carefully shaped electric or magnetic fields. A simple example you already know is probably an LCD screen, right? Liquid crystal display.
Right, on my monitor or TV.
Yeah. The liquid crystals inside change how they line up when you apply an electric field, and that changes how light passes through them, creating the image. That's a basic form of externally controlled matter. More advanced examples might include shape memory alloys metals that snap back to a preset shape when you heat them, or electroactive polymers that bend or stretch when you zap them with electricity. The second school of thought is definitely more ambitious. It proposes that the material itself is actually made up of a whole bunch of tiny, individual, computationally aware units.
Computationally aware units, like tiny computers making up the material.
Sort of, yeah. These tiny units, sometimes called katoms for configurable atoms, or voxels, like 3D pixels, are designed to interact with each other, to dynamically rearrange themselves to achieve some overall collective behavior or to form a specific macroscopic shape. This is the idea behind concepts like modular robotics, where lots of small robots link up, and the really far-out vision called claytronics. Here, the material isn't just passively reacting, it's actively computing and changing its own structure based on a program.
That is genuinely mind-bending. Little robots building the material itself. So how are scientists actually trying to make this happen? What are the practical techniques they're using in labs today?
They're using several really innovative methods, kind of pushing the edges of material science and engineering. One key approach that bridges the gap between static objects and dynamic ones is 4D printing.
4D. What's the fourth mention?
Time. It extends traditional 3D printing. Instead of just printing a fixed object, 4D printing uses special smart materials. Things like shape memory polymers, hydrogels that swell or shrink with water, certain alloys. These materials have the built-in ability to change their shape, their properties, or how they function over time, usually triggered by an external stimulus like heat, water, light, maybe even changes in pH.
So you print something flat, and then it folds itself into a box later.
Exactly. Imagine printing a flat sheet that then automatically folds itself into a complex 3D structure when you, say, put it in warm water, or a medical stent that's printed compressed, but then expands to the right shape inside the body when it reaches body temperature. It lets you create objects that can self-assemble, maybe even self-repair, or reconfigure after they've been printed. It goes way beyond static 3D printing.
That's incredible. Objects that build themselves after they're made, like bringing blueprints to life.
Another really interesting area is the design of metamaterials. These are engineered structures where the amazing properties come not so much from the chemical makeup, but from the precisely designed geometry or internal architecture, usually at a scale smaller than the wavelength of whatever you're interacting with, like light or sound. By arranging tiny structures and clever patterns, engineers can get materials to behave in ways not found in nature, like bending light backwards or having weird mechanical responses. For programmable matter, some researchers have shown that if you take a sheet patterned with cuts inspired by kirigami, the Japanese art of paper cutting and folding, you can apply tension and precisely control its shape, its stiffness, how it bends, in a very predictable, tunable way. The function is literally programmed into the physical cuts and folds.
Okay, so programming the shape itself, and then there's modular robotics, which sounds like those tiny computing units actually working together.
Right, that's maybe the most direct and visually striking example of programmable matter concepts in action. Modular robotics. These are systems made of many individual, often identical, voxel-like modules. You might have heard of projects like MIT's M-blocks that jump and stick together, or Harvard's kilobots, which are thousands of tiny, simple robots, or EPFL's roombots that look like furniture components.
Yeah, I've seen videos of those cube things climbing over each other.
Exactly. They're designed to self-assemble, maybe pull themselves apart, and reconfigure into different complex shapes to do different jobs. Each little module might be pretty simple on its own, but when they communicate and cooperate, they can form incredibly adaptive, versatile, and resilient systems. This is amazing for robots that need to work in unpredictable places like search and rescue in a collapsed building, exploring hazardous environments, or maybe monitoring infrastructure where the robot needs to change shape to crawl through pipes, then climb a wall.
Okay, here's where it gets really interesting. You're talking about a robot that could literally rebuild itself. Change from having wheels to having legs to being like a snake all by itself. Have people actually built things that can do that? Even simply feels like so much of this programmable matter stuff is still firmly in the science fiction category. But are there actually tangible examples we can point to today? Where are these ideas showing up, even in simple forms?
Oh, absolutely. Even if the full Claytronics vision is a way off, the underlying concepts are definitely being applied now in simpler ways. For example, think about adaptive clothing. Maybe not fully morphing suits yet, but garments with magnetic closures that make them easier to put on for people with limited dexterity. Or fabrics that change their thermal properties based on temperature or moisture. That's a simple but powerful example of a material adapting its function. It can make a huge difference to someone's independence and quality of life. In industry, you're starting to see patents and prototypes for reconfigurable robotic arm systems. Arms with joints that can be adjusted and locked in different configurations. These let factories tackle different complex tasks with more flexibility, without needing a whole new specialized robot for every single job. Increases efficiency, reduces cost.
Okay, so practical uses are emerging. But the future vision, that really does seem to stretch into the wildest sci-fi dreams, doesn't it? Where could this ultimately take us?
It really does. The long-term potential is staggering, touching areas we usually see in movies. Imagine morphing aircraft wings. Wings that could dynamically change their shape during flight to optimize lift and drag for different speeds, altitudes, or maneuvers. That could mean much more fuel-efficient flight, more versatile aircraft.
Wings that change shape in the air.
Wow. Or consider the military interest. They're very keen on the idea of a universal spare part. Imagine having something like, well, a paint can filled with tiny reconfigurable particles, and you could just tell it what part you need a wrench, a specific bracket, whatever, and it forms itself into that tool or part on demand.
A universal spare part.
Yeah.
That would totally change logistics, especially in remote places. No need to carry every possible spare.
Exactly. Revolutionize maintenance and repair. And then there's that really ambitious, almost philosophical vision of Claytronics from Carnegie Mellon. Their goal is to eventually create tangible, interactive, physical objects made of these tiny atoms. Objects you could literally mold with your hands, pass around a table, maybe even have change color or texture in real time. Imagine holding a 3D model of a building design, physically reshaping it, and having your colleagues see the change instantly, or maybe interacting physically with virtual characters. It's a whole new way of thinking about human-computer interaction. And if you really connect this to the bigger picture, it starts to challenge our fundamental definition of what a physical object is. We tend to think of matter as fixed, static, defined by its inherent properties. Programmable matter suggests a world where form is fluid, dynamic, responsive, maybe even intelligent. It's a truly profound potential shift in how we might interact with our physical reality, moving from just being passive observers to maybe active participants in shaping the world around us moment by moment.
Intersecting frontiers in critical analysis.
Okay, so we've explored graphene, aerogel, and programmable matter on their own, which is fascinating. But here's where it gets maybe even more interesting. You hinted at this earlier. What happens when these amazing materials don't just exist separately, but actually combine? Does the real magic happen at the intersection?
That's often where the most exciting breakthroughs occur, yes, at those intersections. When you start hybridizing these new materials, take, for instance, graphene aerogel. This is a perfect, really compelling example of that synergy. You take graphene with its incredible strength, its amazing electrical conductivity, its huge surface area, and you combine it with the structure of aerogel, that ultra-porous, super light, low-density network. What you get isn't just a slightly better graphene or a slightly better aerogel. You create an entirely new class of material with a combination of properties that was basically unimaginable before.
And the properties of these graphene aerogels, they sound completely off the charts, like something engineered for a sci-fi movie prop.
They really are remarkable. Graphene aerogels have actually been made that are claimed to be the world's lightest 3D printed structures, weighing as little as 0.16 milligrams per cubic centimeter.
We heard that earlier, 7 times lighter than air.
Exactly. Yet, despite being mostly empty space and incredibly light, they can be proportionally stronger than steel at only a tiny fraction of its weight, like 0.2% of steel's weight.
Lighter than air, stronger than steel. That's just paradoxical.
It really is. And they're not just light and strong, they can also have amazing elasticity. Some could be compressed by like 90% and still spring back to their original shape perfectly. Imagine crumpling up a solid material like paper and having it pop back into form. These unique combinations make them incredibly promising for things like high-capacity supercapacitors, maybe batteries that charge super fast, and environmental uses too, like soaking up oil spills very efficiently because they're so light and have that huge surface area and tend to repel water but attract oil.
Okay, the implications there are really exciting. It really does suggest we're just scratching the surface. Combining the best features of these revolutionary materials could lead to totally new functions, things we couldn't achieve with just one component. So to help everyone listening kind of pull this all together, let's zoom out for a second. Do a quick side-by-side comparison, just the essence of each material. For graphene, the main job seems to be high-performance electronics, energy storage, sensing, right?
Exactly. Key properties. That single atom thickness, the crazy high electron mobility, 200,000 centimeters of each, was highest thermal conductivity, 3,000, 5,000 WMK, and that extreme strength, 1 TP Young's modulus. But the main challenges, still high production costs, getting the scalability and quality control right, and dealing with potential environmental issues from some production methods. Key applications we're seeing, flexible screens, faster batteries, better solar cells, biosensors, water filters. Commercialization stage, still nascent. Definitely high growth potential, but facing real hurdles for mass adoption.
Okay, then aerogel, primary function, super insulation, making things extremely lightweight.
Right. Key properties. Ultra porous, over 90% air, extremely low density, 0.0003 GCM, and that ultra low thermal conductivity, 1550 mWMK. Challenges. Still high initial cost, those complex manufacturing steps like supercritical drying, and sometimes it can be fragile, though they're working on tougher versions. Key applications. Building insulation is huge. Aerospace thermal protection, high-performance clothing, and that cool cosmic dust capture. Commercialization. It's expanding. Seeing more use in specialized areas, and demand is growing thanks to green building rules and energy efficiency pushes.
And finally, programmable matter, primary function, reconfigurable shape and function, things that can change.
It's exactly. Key properties are dynamic. Shape-shifting, property-changing, reconfigurable structures. Can be active-driven or passive, responsive. The challenges here are pretty immense. Huge complexity in design and control. The technology is still very young, mostly R&D. And there are significant ethical and safety questions, especially around autonomous robotics. Key applications are still mostly future-facing. Maybe 4D printed adaptive prosthetics, self-rebuilding robots, adaptive clothing, that universal spare part idea, commercialization stage. Mostly conceptual still. Real-world uses are just starting to pop up in very specific niches, like some adaptive clothing features or advanced research robots.
Okay, that's a helpful snapshot. But beyond just the tech specs and the challenges, these materials, especially programmable matter, raise some really deep questions about our future. About society. Let's touch on those ethical implications. You mentioned self-reconfiguring robots, potentially for military use. That seems like a really difficult dilemma we need to think about carefully.
It's absolutely critical we discuss this openly and proactively. On one hand, yes, using autonomous robots in conflict could potentially reduce risks to human soldiers. That's a strong argument from a certain perspective. But the counter-argument is equally serious. If you lower the human cost of war, do you inadvertently lower the threshold for starting conflicts? Does it make going to war seem easier or less consequential?
That's a chilling thought.
It is. And then there's the whole issue of autonomy in lethal decision-making. If a self-reconfiguring robot makes a mistake in combat, maybe identifies the wrong target. Who's responsible? The programmer, the commander who deployed it, the machine itself. Our current legal and ethical frameworks just aren't equipped for these questions yet. Ethics, law, policy. They need to evolve alongside the technology, not trail decades behind. We need that conversation now.
And then there's the even more mind-bending side of programmable matter, things like claytronics, potentially blurring the lines of reality itself. You said it challenges our very definition of a physical object. That sounds like it goes into really deep philosophical territory.
It absolutely does. This is where engineering meets fundamental philosophy. If we reach a point where matter can be programmed to be responsive, maybe even aware in complex ways, if claytronics can create virtual entities or simulated realities that feel completely real, what is their status?
What rights would a computational being have?
Exactly. Is it just a sophisticated tool, an illusion? Or does sentience itself become something you can program? What does harm even mean when applied to something that's fundamentally made of information, not biology? These aren't just abstract thought experiments. They force us to grapple with core questions about consciousness, identity, reality, responsibility in ways we've never had to before. Our existing ethical frameworks built around biology and human experience just don't map directly onto this. We're going to need new ways of thinking, new principles developed alongside the technology to navigate the profound power and potential risks involved.
Yeah. It really underscores that this isn't just about cool new gadgets or more efficient materials. It means we, as a society, have a huge responsibility to actively discuss, debate, and guide how these incredibly powerful technologies are developed and used. The future they enable will depend heavily on the choices we make right now. Outro. Wow. We have covered a lot of ground today. A really deep dive into 3 materials that aren't just changing technology, they seem to be fundamentally reshaping what's even possible in our world. It's been quite a journey.
It really has. We looked at graphene with those unmatched 2D properties, set to potentially redefine everything from electronics to energy. Then Aerogel, the master of being porous and lightweight, offering this incredible pathway to radical energy efficiency and sustainable design. And finally, programmable matter in all its different forms, challenging the very basics of how we think about and interact with physical objects, hinting at a future where things are fluid and responsive.
Yeah, from making your phone screen maybe finally unbreakable and flexible to keeping your house warm using way less energy, maybe even creating tools out of thin air that can adapt to any job. These materials aren't just lab curiosities anymore. They feel like the actual building blocks of tomorrow. We're seeing their impact now, and they're hinting at a future that, honestly, still feels pretty sci-fi.
And we saw that all 3, despite being so different, face some similar big hurdles, right? High production costs are a common theme, challenges with scaling up manufacturing while maintaining that crucial quality control, and navigating the complex environmental or ethical questions that come with powerful new tech. Overcoming these bottlenecks in manufacturing, in cost, in responsible deployment is absolutely key for them to be widely adopted. But the good news is the market interest is clearly there, the growth projections look strong, and there's significant investment happening, both private and public, recognizing just how transformative these materials could be.
But maybe one of the biggest takeaways, as we saw with things like graphene aerogels, is that the truly revolutionary potential often lies not just in one material alone, but in how they can converge and work in this single critical material. It seems much more likely to be about understanding how these different advanced materials can interact, combine, create these powerful synergies that lead to functionalities we can barely even imagine today.
Absolutely. And critically, weaving through that whole story from the lab bench right through to societal use is that thread of ethical and societal responsibility. It's not something we can tack on at the end. A holistic, thoughtful, responsible approach to innovation isn't just nice to have, it's essential. It's the only way to ensure these incredibly powerful, transformative materials are actually used to build a future that's more sustainable, more efficient, and fundamentally more ethical for everyone, and that we avoid creating new problems while trying to solve old ones.
So as you go about your day to day, maybe you're holding your phone, thinking about the energy heating your home, or just looking at the objects around you, here's a final thought to chew on. If matter itself can potentially be programmed, designed to change its most fundamental properties, dynamically adapting to the world or to our intentions, how might that fundamentally challenge our understanding of what's real, what's permanent, or even what's truly possible? What kind of world will you help imagine and maybe even build with these incredible evolving tools?